Okay, we're going to talk about random forests. The basic idea behind random forests is we're going to take simple classifiers like short, like trees, and then we're going to aggregate them by averaging the classifiers. So if you think about f hat sub b as being a different predict method, the result of a different predict method for each classifier. So specifically, if we think about decision trees, to calculate f hat of x for a given decision tree, you are going to feed in the x and choose which side of the appropriate splits it goes on until you hit a leaf node. And then that leaf node is going to have some predicted y. And that will be your f hat sub b, or it's going to have a predicted probability, whatever the output of your classifier is, or your decision function or your regressor is. Now, we're going to assume that we have multiple trees instead of just one, and then we're going to aggregate them just by summing and weighting these base classifiers. So in practice, you would just apply the predict method for the multiple classifiers and then average the outputs for a given new x. And it'll be a weighted average, weighted by some weight alpha sub b. So for example, you could set all the weights to be the same, and then this f hat of x would just be the average of all the base classifiers. Now, what is the effect of this if the base classifiers are trees? So let's think about this red and the blue decision trees here. So these are depictions of different possible splits that we could have made for our given based on a given data set. Now, some of these splits are different in terms of which axis they use, and that's a good thing because then when we average, we're going to get something novel from this. So in the numbers that are listed here in red, these numbers are the output. So the f hat 1, for example, this is f hat 1 of x are these numbers, and this is f hat 2. Right? And we're going to think about just averaging these two f hats. So what that means is if I was to give you a new point here, then your prediction would be 1 for f hat 1. And here would be prediction 1/2, and then to get the output aggregate f hat, you would just average these two outputs. So that's the average of 1 and 1/2. That should be 3/4, which is what you would get here. Right? And so if we just imagine doing that for the entire space, we would get a division into regions that have the following labels. So we have 3/4 in the rectangular region that we said before. Now, this split would further make two different splits. One would be a split which would give you the 5/12 here and 1/2. And then here you would get a 1/4 and a 1/6. To verify that, the average of, for example, 1/2 and 0 is 1/4. Down here you have the average of 1/2 and 1/3, should be 5/12. Let's just verify that. And then here you have the average of 3/4 and 1/3, and so on. So this is our the way in which we can average two different decision trees. And in practice, we would just evaluate the predict functions for each decision tree and then average in the end. And this image is a little bit confused. This line here really should be up exactly where this line is. Something like this, for this to be true, for this to be correct. Okay, so that's the idea behind how you do predict with aggregates, and so so why would we do this, and why would we hope that aggregation would help? Well, let's think about the bias of this f hat of x and y. So the bias term is the expectation of this f hat b of x minus y of x minus y. Right. This is our bias. Right. Oops, sorry. So we're just going to consider the bias of the aggregate in terms of the bias of the individual components. So in this example that we had before, we have that this bias of the average of the f hat 1s and f hat 2s. It's just going to end up being the average of the biases. So f hat 1 of x minus y, and just by plugging in what f hat is, plus 1/2 expectation of this f hat 2 of x minus y. Right? So this is the bias. And so if we imagine that these biases are the same here, right, or are sort of comparable, then we're just going to get that the bias isn't reduced, but it's also not increased by doing this averaging necessarily. So we're going to think of this as sort of indicating that the bias is unphased, unless, of course, you have multiple decision functions that where one of them is a smaller decision function, and then the addition of it reduces your bias. But we're not going to expect that our bias is going to be decreased, but we're also not going to expect it's going to be increased either, because you don't necessarily have control over that. But the variance, if we think about the variance of our estimate, so we have the expectation, or let's just consider the variance. Let's suppose something that's not going to be exactly true, but let's just suppose the following thing: that y hat 1 and y hat 2 are independent of one another. That these predictions are independent of one another. Then the variance of f hat of x, this is equal to the variance of 1/2 f hat 1 of x plus 1/2 of f hat 2 of x. Okay. But then because because you're multiplying the variant just due to independence, this is equal to 1/4 times the sum over the b's of the variance of f hat sub b of x by independence here. So this is not going to be a realistic assumption, this independence, but if it were true, then we're actually going to reduce the overall variance by a factor of 1/2 in this case, and that's just going to get more extreme as we increase the number of decision trees here. So we're going to keep this in mind, because you could possibly get a significant reduction in variance by this aggregation procedure without reducing bias. This is very informative because we're going to use these ideas to select our random forest procedure. Okay, so the big question in your mind should be, how do we get multiple decision trees? So to do that, we're going to use bagging. And the basic idea behind bagging is you're going to take your data set and you're going to sample it with replacement. So we're going to select, say for example, a bunch of these positive samples, and some of the positive samples are going to get selected twice, or 3 times, or 4 times, right? Such as the one underlined here. And same with the negative samples, and some are not going to get selected at all. And then if we repeat this procedure, we're going to get a different data set with multiple counts. Now, if we apply our procedure to each of these different bag samples, so these are sometimes these are called bootstrap samples or bag samples, we're going to possibly get different decision trees. Okay, so the basic idea behind bagging, and this sampling of the data set without replacement is called bootstrapping. So the basic idea behind bagging is that you get bootstrap samples, which is just sample with replacement, sorry. Samples, call it just D1 up to D capital B for the different data sets. And then you train your F hat sub B on calligraphic D sub B. And you could imagine what you would do if you had multiple copies of the same sample. You would imagine you would just use it as if there were multiple data points on top of one another there. And then at the end, we just average our F hat B's, right, in the way that we described above. Okay, so how can this relate to the bias-variance trade-off that we had before, that we mentioned before? So first of all, how do we choose or how do we reduce our bias? Well, first of all, nothing about this bagging procedure is designed to reduce bias. So what we have to do is just choose a base classifier with low bias. So that's the only thing we can really do. We choose a base classifier with a low bias. Now, in the context of decision trees are going to have low bias if you're going to grow its depth quite a bit, right? Because bias will decrease as the number of data points in the rectangular regions are going to decrease, right? Or as the rectangular regions get smaller and smaller, right? Because if they're very small rectangular regions, then you don't really have to interpolate that far to get between your prediction and the point you would like to predict. So, or between your data and the point you would like to predict. So we're going to choose a large depth, a very large depth decision tree. So that's the first bit of intuition that we're going to use to decide how we're going to create our random forest. Now, how can we reduce our variance? Can we reduce our variance? Right? How do we reduce our variance? Well, the way that we're going to do that is we're going to try to make these bootstrap samples as much non-overlapping as possible. So we're just going to reduce our subsampling rate and then increase this capital B, the number of bag samples. So subsample rate, when I said sample with replacement, I didn't mean we had to sample exactly the same number of data points as in the original data set. We could sample much fewer data points, so some fraction of the data points. And if you subsample a fraction of the data points, you can imagine that the resulting data sets are less and less dependent. So this is sort of a hand-wavy argument for how we reduce our variance, but it's important to understand this because you're going to select some of these tuning parameters. So we reduce our subsampling rate. To make the different classifiers less dependent, and then we increase B. So these are the two things that we can do. And then random forest is just the combination of these things. So random forest algorithm the basic idea is that for little b going from 1 up to capital B, we just bootstrap. M rows with replacement. Right. And then we sample. So this is an additional step that I haven't mentioned yet, but this is also in this. So we sample D predictor variables of the possible capital P or lower P predictor variables, and then we grow a nearly or a max depth tree. So sometimes we set this to be max depth, or we can select the depth of the tree, but typically we make it a very deep tree. So I'll just write nearly up here. A nearly max depth tree. And this is on the M by D dataset. Because we've subsampled our predictor variables and we've selected our rows, we actually this might run very quickly because it's on a much smaller data set. Because the complexity of a decision tree scales linearly with M and D. And then after this, we save our trees, and we also have to save the frequencies or the bootstrap frequencies. Right? So how often was a data point used? Right? So that's random forest. And then at the end, we predict with our aggregate. 1 over capital B, sum, I equals, or little b equals 1 to capital B of f hat sub b of x. Right? We have a bunch of trees, so we can predict, and we can just average the predictions. Okay, so why did we save the sample frequencies? So one thing is we can use these to calculate the out-of-bag error. And the out-of-bag error is just going to be a measure of our test error, because quite often a sample is not used in a bootstrap sample. A data point's not used in a bootstrap sample, so we can think of that as a natural holdout. So for each xi and yi pair, for each of these, we can let capital BI be the bootstrap samples without I. Okay? Then we can predict with our y hat I naught, which is equal to this 1 over the size of capital BI, sum of B within BI of this f hat sub B of xi. Right? And so this is just the prediction using all of the bags that did not include the point in question. And then we get to compute our out-of-bag error. So this is one of the nice consequences. Which is just our average loss using this out-of-bag prediction. Okay, so that's one of the nice consequences of random forests, is that we get something which is naturally the out-of-bag error. Another thing that we naturally get are measures of how important the predictive variables are, and you'll see this in if you use a variable importance scores that come out of random forest. Because we sample the predictor variables, we get to see how often predictor variables were used within the random forest as a splitting variable. So it doesn't necessarily, we don't necessarily require to sample the predictor variables to get this, but there's a lot of very intuitive scores that come out of this, such as variable importance. So that's random forests. There's a lot more to be said about random forests. Because you sample these D predictor variables, sometimes you can mitigate the effects of the greediness of decision trees. So for example, if due to variable correlations, you're always you would always be splitting along maybe a suboptimal direction in a decision tree. Because we subsample the predictor variables, oftentimes that suboptimal direction is not going to be sampled. And so that's some of the intuition behind sampling the predictor variables as well as doing the bootstrap samples. And it's likely that it just was observed to give you good performance, the sampling the D predictor variables. So that's the extent of what we're going to talk about regarding random forests. So the only thing left really to say about ensembles of trees is boosting and Adaboost.